In standard neuroscientific research, the spontaneous eye blink is a nuisance. To study subtle cortical activity, researchers must scrub EEG data of massive electrical interference. Because eyelid muscles generate a much larger electrical potential than the brain itself, these spikes are easily isolated across frontal channels like FP1. Current protocols involve identifying these high-amplitude artifacts and deleting them from the final record. Every blink is a complex behavioral output, modulated by the central nervous system. The discarded Vertical Electrooculogram, or VEOG trace, contains a highly sensitive, non-invasive biomarker. It provides a direct readout of human anxiety. The biomechanics of the eyelid are driven by the orbicularis oculi muscle, which is innervated by the facial nerve root. While the blink functions as a maintenance reflex to lubricate the cornea, its timing is regulated deeper in the brain. The primary blinking center is housed in the globus pallidus and is heavily modulated by dopaminergic pathways in the striatum. Because these neural pathways are deeply integrated with the brain's affective centers, cognitive and emotional states directly alter the physical execution of the blink. This basic reflex inherently encodes complex psychiatric arousal states. To capture these states, researchers place electrodes above and below the left eye to record the eyelid's muscular action potential. Subtracting the lower signal from the upper cancels noise, yielding a clean baseline with one distinct peak. A 250 millisecond window isolates the physiological event. Blink amplitude is the peak voltage, measuring physical magnitude and speed. The timing between closures is the interblink interval. By calculating the coefficient of variation within these intervals over time, scientists derive blink rate variability. This quantifies how rhythmic or erratic the blinking pattern is. Extracting these three parameters allows researchers to quantify the physical strength and rhythm of the eye, capturing physiological data that a simple blink count ignores. The acoustic startle reflex is already established as a gold standard psychophysiological marker for anxiety. However, traditional startle testing is restrictive. It relies on aversive auditory stimuli and highly controlled laboratory environments that can interfere with a subject's baseline state. Fear and anxiety activate the amygdala, which stimulates the brainstem's reticular formation. This pathway drives stronger, more rapid contractions of the eyelid muscles. Extracting blink amplitude from spontaneous activity utilizes this same neural hardware. It provides comparable data on arousal states through passive, non-interfering observation. To validate this metric, researchers compared a 5-minute unconstrained resting trial against a focused visual task. At rest, blink amplitude shows a moderate positive correlation with state anxiety, yielding an R value of 0.288. This baseline data is limited by massive interpersonal variance. Without an external focus, subjects succumb to mind-wandering and internal distractions. In the second trial, subjects watched 36 minutes of emotional film clips to focus their attention. When visually constrained, the correlation between blink amplitude and state anxiety nearly doubles to an R value of 0.557. Under these focused conditions, overall blink rate and blink rate variability also become significant statistical predictors of a subject's anxiety level. High-state anxiety produces faster, stronger, and more uniformly rhythmic blinking, but this signal only emerges clearly when environmental visual variance is eliminated. A subject's baseline personality, their trait anxiety, does not drive their physiological output directly. Instead, trait anxiety shapes how a subject experiences their immediate environment. This situational experience, state anxiety, is the proximate driver of the blink response. The blink trace is a real-time reflection of current affective distress. It functions as an indicator of current state rather than a permanent psychiatric diagnosis. Because environment modulates the signal, researchers must account for the mechanical demands of visual tasks. A normal resting blink rate is roughly 17 times per minute. When focusing on a digital screen, this rate drops to just 4 or 5 blinks per minute. This heavy cognitive load overrides the limbic system's anxiety signal. Effective experimental design must balance visual constraint to isolate the signal without inducing the digital eye strain that suppresses it. By altering data processing pipelines to measure VEOG amplitude, researchers gain a direct readout of the limbic system. This method provides the psychophysiological efficacy of traditional startle reflex testing, while using standard EEG hardware instead of specialized noise generators. When the visual environment is strictly controlled, the spontaneous blink ceases to be a data artifact and becomes an accessible readout of human arousal.